Here we are again. Our textbook, Logics for Computer Science, Classical and Non-Classical, Springer, 2019. Anita Wasilewska, it means I am the author. So now we are in chapter 8. And chapter 8 is a shorter chapter. It has 4 parts. And it really is a but good, correct formalization of intuitive approach to predicate languages and semantics, which we covered in chapter 2, which I promised that we would do a formal, the formal version, a totally formal version of it. So, of course, we start with formal predicate languages, and to remember that predicate languages are also called first-order languages. And predicate logic is also called first-order logic. And so you can use both those terms in books and in literature. And we work with different predicate languages depending on the application. So we'll talk, but what those all languages have in common is a certain features which we are going to define one by one. So predicate language is, I'm going to write it because that's what L, predicate language now is as before alphabet, as before set of formulas. I'll put it here, set of formulas, but we add a new set, T. I use also the fat T because this is the way we, a lot of books and literature use the fat T for the set of terms. So alphabet, and this is new set, which is set of terms, which we have to define, this is a new, and formulas is formulas, which has a little bit more complex definition, but it's still the same type of definition. So, of course, because the language is much richer, we have alphabet is much richer. And alphabet has predicate variables. Now, the variables are called predicate variables, and we will denote them in different way. Propositional connectives. So really, in the language, we'll have all propositional connectives. We have parentheses as before. And now we have quantifiers. And we have a special sets, which are P is predicates, P predicates. So there are new elements of the alphabet. F predicates correspond to relations in the real world. F, I try to write it, F are a set of functions or functional symbols which corresponds to the functions. And we also have, which we see is set of constants. So we have, and also, of course, we have Q, which is a new thing, is the set of quantifiers. So we have, and of course, they are all disjoint. We also assume, because we want to prove the completeness of predicate logic in the most general case. So we assume that all these sets, predicates, function, constants, are countably infinite. And then in particular cases, they can be whatever we want them to be. And also the variables, of course, I didn't put it here. V is variables. the set V of variables, which is also countably infinite. And now variables, I predicate functions. So at variables, we now write, we use x1, x2, x3. We use the x's instead of ABCs to distinguish them from propositional variables, which represented sentences, and variables would represent the elements of the universe. So they are really like real x's in a sense. They represent real x's when you use in mathematics. That's why. And of course, you have propositional connectives, as we did before, one argument and two argument connectives, and quantifiers. So quantifiers, we adopt two quantifiers. And we use the notation, for universal quantifier, and this for existential quantifier. So we use this notation. There are different notations and so on, different symbols. These are our symbols for quantifiers: universal and existential. And I say this how I will use differently. Books use different symbols, but these are the most common symbols, and we use them. And another thing which is important, in case of classical logic and the logic that extend it, is possibly to adopt only one quantifier, because they are definability. Remember, we had definability of connectives. Now also we have definability in classical logic. You have definability of quantifiers, but we will use both of them because it is more convenient. That really describes the way we do our mathematics or the way we think. So we want to have both of them. For the same reason, we adopted the full set of propositional connectives for the propositional logic. And now, predicate symbol, as I said, they represent relations, and we denote them is countably infinite set. We denote P, Q, R, and so on, and we write P number. This is number of argument in the predicate n, so we call it P is n array predicate symbol. So it's the same for the functions, and we use the symbols for the functions like we do in mathematics, FG, etc. And the same we say how many arguments the function, but these are not functions, they are symbols which correspond in real life to the functions. And constant symbols correspond to elements of the universe, to the constant, so it's the same. And so what really distinguish one predicate language from the other is the choice of those sets. As I said, in full logic for our completeness theorem, that those sets of predicate, function, and constant is countably infinite. But when you talk about particular languages in particular applications or theories, we have to specify them. So we now write the language, predicate language. We would write that our L depends, we specify P, we specify F for functional symbols, predicate symbols, and constant. And of course, we also have our connective added because they are all based on connective. So any predicate language is determined by connectives. There's choice of predicate symbols, functional symbols, and constants. Now, of course, we talk about predicate languages, which we already had on slides, but to to be able to say that it's predicate language, we have to assume that all predicates, so the symbols which represent relations, is non-empty. So we need to have at least one relation. And of course, we can have that F can be empty and C can be empty. So we can have, for example, a language which would have P empty. Empty is still a predicate language. And con are propositional connectives. So for example, we can have, if we write that L equal P Q F empty, and whatever are the connectives, they are propositional connectives, it means that this language has two predicates symbols. And we have to say how many arity. For example, if I write this, it means this predicate symbol has two arguments, and I say that that predicate symbol Q has one argument. And also I have one functional symbol, so I say that this functional symbol is, for example, has two arguments. And so this is a particular language, and this is a general form of language. And in general, again, I repeat, for the completeness theorem, we would assume that all of them are non-empty and countably infinite. OK, hop. And we write, of course, the predicate we write as px and so on like we do normally. And so now we have the language is alphabet, terms, and formulas. So we have now to define what are those term sets and what are the set of formulas. And connective, I already said, remember the connective, we assume that connectives are C1, C2. So we have a connective with one argument connectives and two argument connectives. So for example, we can have language which I say, for example, negation and implication. Let's put, this is a general form, is con. And here I put, as connectives, I put negation of implication. So this is a particular predicate language, right? So this is a general form, and here's particular predicate language when you have two connectives, negation of implication, and we have two predicates, one functional symbols, and no constants. And now we have to define general definition. So this is our notation. And remember, the general definition, L, is alphabet, which we all defined, set of terms and formulas, right? Terms. I repeat because this is a new word, and now we have to define what is the set of terms and how, and of course, what is set of formulas. So we extend the definition of set of formulas, of propositional formulas, into the predicate formulas in absolutely traditional way. So now terms. And this is important definition. So set of terms of the predicate language. And I don't write these connectives because when they are fixed, you just don't need to write connectives. So they are the connectives. Of course, each language has propositional connectives. So terms are the smallest set of finite sequences of alphabet. What? Variables are terms, those x1, x2, etc. Any constant symbol is a term, so all constants are included in terms. And if f is n-place functional symbol, it means the number of arguments of f is n, and you already have n terms, you can write f in front of those terms. So, so that is like really how you write function and composition of functions. For example, let's say that you have f is one-place functional symbol, and you have like two variables. It always has infinite number of variables. This is an example that we have two variables, and we use CD for constants. So again, remember, so now variables are, because, you know, we cannot use all the time different symbols. So now variables, just to remember, is x1. We denote variables by x's, countably infinite. And constant, C, constant, we, if denote by A, B, C1, C2 for constant. So now those letters, or if you have infinitely many of them, so now those letters, small letters, denote constants in our universe. So variables are by x's and constants are ABCs. So now if you have two, for example, let's take two variables. So this is a term, variable is a term. Now you put the f is one place, so you put f in front of variable. You can put f in front because constant is already a term, so you can put f in front, and then you can alliterate and so on. You have countably infinitely many. And for example, now we can have a language when f is empty. So let's take now the language that, remember, that is empty. Always to have a predicate P, the set P is non-empty, remember? Because to call it predicate, you need to have at least one. So now, if you say, have a language that f is empty and C is empty, C constant empty, so it means you have the language which have, I skip the connective because I don't at this moment list them, and you have P and you have empty, empty, so which would be the terms. So the terms, by definition, the terms of this language would be just variable, there's no functions, and the first all variables are terms. So you can see the set of terms is always non-empty because we have non-empty and countably infinite because we have infinitely many variables. So here the set of terms would be just variables, which would be x1, x2 countably many. So you can see that always the set of terms is in this language, or in any language really, the set of terms is non-empty for any language, predicate language, because each language contains countably infinite set of variables. And there's more. If you have two symbols, one I say is one argument, and they correspond to functions. So you can imagine that's why we use FG. So one argument functional symbol, G is two argument, and you have two constants. So for example, the terms would be here you have this is a term, you have x is a term, y is a term, you put g because it's 2 argument, and then you put f and so on. So the terms, it's like, it is a structure of writing of composition of functions. And okay, so atomic formulas. Now we want to define atomic formulas like we did in propositional case, right? Atomic formulas, what it was, variables are atomic formulas. So atomic formulas are the simplest formulas, and they are building blocks of other formulas on the way of the propositional variables, on a way that propositional variables were in the case of propositional languages. So what is atomic formula? Atomic formula is like the simplest formula. It means atomic formula, and remember, we always have P must be non-empty. So if you have R in P, relational symbol, and let's say is an argument, R of x T1 Tn is atomic formula. This is relational symbol acting on terms. You know that the set of terms is always non-empty. So in a particular case, if there's no functional symbols, that would be R of x1, xn. So this is, and for T1, Tn are terms. So these are like building blocks, relation between those terms, and you have the set of atomic formulas is the set of R, T1, Tn. This is what the sequence of, finite sequence of sign of the alphabet, such that R is in P and T1, Tn. So atomic formulas is always non-empty and countably infinite. Why is non-empty? Because P is non-empty. So there's at least one R, and T set of terms is also non-empty because all variables are terms. So you have, and there is infinitely countably many terms. So you have always you have infinitely countably many formulas. So, and here I already wrote on the blackboard, there are different examples. For example, P empty, empty, P is 1, and you have the atomic formulas would be just variables. And there's another language, you list, this is R, and you say this is one symbol, there are two functional symbols, and there are two constants. So we had, and you have now examples of different languages. And then we, in general, the set of formulas. So this is the set of formulas definition. Now we have a predicate language. We have a connectives. Whatever are the connectives, they are unary and binary. And and now we define the set of connectives of formulas in normal way. But first is atomic formulas are formulas. So now atomic formulas are those R's. So atomic formula is formula. And then when you have a one argument connective, you write as we did in propositional case. And then if you have binary connective, you write as a propositional case. So that is exactly repetition of propositional. And now we have also quantifiers in our alphabet. So if you have a quantifier, and x is any variable, a formula, you can put the quantifier for all x, and quantifier in formula always comes with x. So the sign of quantifier, this is our symbol of quantifier, but in the formula, you have always to write for x and a when a is already a formula. And the same, x is any variable, so y a is a formula, so x1 is a, is a formula, etc. So remember, in this definition, x is any variable, so you don't need to distinguish them. Can be x, can be y, can be anything. So now, when you are here, we have the notion of a scope of quantifier. And so remember that in formulas, quantifier always comes with x. So this is a formula, and scope of quantifier, scope of our quantifiers is that okay, the scope, you say that if you have this, A is in the scope of quantifier. Formula is in the scope of the quantifier. No, but formula is a concrete formula. Remember, we had that if the formula A is A, B, where that was two-argument connective, you can put x in front, and for one O. And when or you have a formula A, when that was the symbol for one argument connective, you can put x. So this is in the scope, that formula is in the scope of this quantifier. This formula with binary connective as the main connective is in the scope of the quantifier. And you can see that parenthesis, that's why we put close the formulas with parenthesis, is the scope of the quantifier. And here the scope of quantifier is everything which is in A. So you can see you don't need to put parentheses around because you know how it looks like. So that is important notion. And for example, here's language. And you have two symbols, etc. And there are some well-formed formulas. And you can see here is atomic formula. Then I put the quantifier existential. And R is, so I don't need atomic formula. So that atomic formula is in the scope of this quantifier. I can put negation, and I can build those formulas recursively. So the next thing, and also here, as I said, we will be studying classical predicate logic. But, so it means our connectives, we can assume that we have all these connectives or any negation of any two of them and so on. So but we can also have non-classical predicate languages. It means you can have, as connectives, you can have different non-classical connectives, whatever you want. You can have P modal connectives and so on. So here you have an example of modal language, and that would be a predicate language with the choice of those tells you which kind of non-classical language it is. So the proper formulas you could use in a similar way as we did classical connectives for modal connectives and so on, but it is, so I just want to tell you that they exist. We are not going to study them, but when you have a modal propositional logic, for any modal propositional logic, we also have a version of modal, if you have modal connectives, of modal predicate logic or knowledge logic and so on. So that is something to remember, but our goal is to study at this moment only the classical connectives and classical semantics and classical predicate logic. And now, and then I also explained the formulas in the scope and so on. The next thing which is important, and I'm going to explain you, that quantifiers bind variables in the formula. So that is, again, important notion. For example, if you have, this is atomic formula, if you put quantifier in front, that quantifier binds the variable y. This, sometimes you can add here the variable x is free. Now, by the definition of formulas, we just built a little bit. Also, we say that we can always write like this. That was a part of our definition of formulas. That was a formula, and that was formula for A being already any formula. So we can have, for example, P, one argument, x, y. This is atomic formula with two variables, and I can put there is z by that definition. X is any variable, so z, x, this x is now z. So, but you can see if you can always put, and then I can put z x1, a nice variable. I can put the quantifier in front, but you can see that this z do not bind any of those variables, or that quantifier. There is x1. For all x1, there is z p xy. That does not bind any variable. So, because we can write such formulas, but what is interesting is the formulas which are bind. So if you put z, you can say that it is formula with a quantifier, but the z does not bind any formula in the and then if I have z here, the z binds that, and y is free, and this binds x, and y is free, and we often write those just to see it. If formula binds, I write it in bold so you can see how, and so this formula binds that. Here, when you look at this, you can see that, let's look at this, right? This x, this is parenthesis, so this for variable binds that x and also this x. And that y binds only this y. So finally, that is well-formed formulas, which is a sentence because all variables are bounded. And so that I wrote you with the fat letters so you can see here. If you write the formula for all x, px, this binds only that, and this y binds only that, and this x is free. So here x is a free variable. Here these are sentences because all variables are bounded. And then it's a proper definition, what are the free variable. So this is definition by example to explain the notion. And here is the definition that FVA, free variables, you have to spell everything. So now you have a proper definition, but you know what it is. And also, we write often, and that we'll be using notation. If you write A, x1, xn, we indicate that free variables of A are inside. So that it's not all free variables, but I say that free variables are some of those AN. And now we have replacement. So there are different operations which are important, and you have to be very, very careful to do those operations. So we can replace x by t. So variable x in formula A, I replace by t, and you write at. So this is result of replacing all occurrences of the free variable x in A by the term. So I will give you an example. For example, let's say for all y, p, x, y in place q, y. This is a proper formula. This is one argument predicate. This is two argument predicate. This is one argument. This is a proper formula. You can see y is bounded. This y is bounded. And this y is bounded. And OK, I will write a little bit more. And p x x. A little bit more complicated formula. This is also complicated formula. Nice. And now I replace. So you can see that this formula, you can say that this formula is A, y is bounded. This bind y has x as a free variable. So this formula, you can write this formula is certain formula with x of free variable. So this is a formula A, the whole thing, which has x as a free variable. And now if you have x, you replace x by t, by any term. So it means you replace all x's in that formula by this term. So let's say, so it means that everywhere, all possible. So here you write t on x, that's why I added, and here you would have all occurrences of x in the formula by t, and that would be a t. So if you do this, remember that that means that you replace all free occurrences of x by t. So that's important. And also, when performing the replacement, we always assume that none of the variables in t occur as bound variables in A. So that is another. I said t is a term, so but I have it's a concrete term. So when we do so, that we assume that none of variables in t occur as a bound variables in A. So, for example, once you have, if t has, you see y is a bound variable, so none of variables in the t occurs at the bound variable. So in this case, none of variables in t can be y. And this is a reminder because that we will use that. You have to be very careful when you replace variables by terms. And there's example why if you don't do that, if you don't put that assumption, you change the meaning of the formula, and that's very important to have that assumption. So that also another important definition is the term t is said to be free for a variable x in the formula A if and only if no free occurrences x lies within the scope of any quantifier bounding variables in t. So, and that is called that t is free for a variable x, and you'll see we'll be assuming that pretty often because we have to be very careful when you substitute something for something to keep the free and bound variables in check. And there's examples. And also we have generalized that definition that if you have a formula and you have formula with n possible n variables, so you can here replace x by t, and you can express each of those variables by certain terms. Of course, they must be that all those terms, when you perform the replacement, must be free for their variables in the formulae. And now, the other important notion, which we already covered in chapter 2, is the notion of restricted domain quantifiers. And so, here is exactly the slide for from chapter 2, because I want that chapter also to be independent. So here is, we already covered chapter 2, so you know that what are restricted domain quantifiers, but I just repeat quickly that in mathematics we often use sentences, all natural numbers are greater than 0 and some integers are equal. So you can write, I wrote here proper formula for all x in n, all natural numbers greater than 0, and there is integer y equal 1. So, and I said, that's my pun on not logic-oriented mathematicians. Mathematician would, and it's okay, right? X greater than 0, and for x in n, and there is y in z, so they just use those symbols just for all there is. So more logic-oriented would write like this, and we would write like that, because now you know that the logic formula with restriction and so on. So, but what it is that those quantifiers, you see, they are not our logic quantifiers, because remember, in logic, quantifiers are just for all x a, and there is x a, that is, x does not belong anywhere, is because eventually it would represent something. So that is important thing to remember. Nevertheless, we use those in our life, in mathematics. We use those quantifiers. We say where x belongs, and these are called restricted domain quantifiers. And the problem is that it's useful to introduce the restricted domain quantifiers, but the law of our normal quantifiers are different. The tautologies or law of our normal quantifiers are different than the restricted domain quantifiers. So, and here is here is how you translate. So when I want to have restricted domain quantifier, So I introduce a restricted domain quantifier for all AX. Not AX is now any formula BX. So it means the restriction is whatever that formula says. For example, I can write for all X natural number in concrete and n greater than 1, X plus n greater than 5. So that would be our restriction, that I look only on natural numbers that are greater than 1, and I want to have x plus n to be greater than 5. So this is a formula which restricts our, and this is our formula bx, and x, this quantifier binds only x, and so on. So, I want to be able to analyze also this kind. And this is the same. By definition, we replace it by, for all x, ax implies bx. And you can see if you write this, this is a proper formula of our language. And for existential quantifier, which has restriction given by this formula, we replace by there is x, a, x, and bx, and you can see, and now this is already a proper formula of. So it is just replacement. You have two, and they are called transformation rules for restricted domain quantifiers, and we use them to prove if any formula with restricted domain is tautological or not, and which are the laws of restricted domain quantifiers. And you have different exercises how to translate. So that was all which we did in chapter 2. So I'm not going to go through it in. I just want to comment on that part. When you translate, you get a formula with restricted domain that represented natural numbers, for example. And then the last step, if you want to retranslate the formula into formula of your predicate language, would be you have to use the formula for restricted domain quantifier. It means you replace this part by for all x, and x implies that formula, and that is n, and that restriction you replace, and this is your correct formula in our predicate language. And of course you can do the short solutions, because shorthand is very useful. You have basic statements, and corresponding atomic formula x in n is mathematical statement. So that corresponds, you write, because I want to remember that is n, so nx for natural numbers, that was, x was in z, y in z, you write zx or zy, and x greater than 0, greater is 2-element predicate, so I use letter G, and then x is a variable and 0 is a constant, and equality. Equality is E, 2 argument predicate, so in logic you would have 2 argument predicate, and y is a variable, and this is another constant because that was a constant, so the statement would be, and you translate. So these are translations. Okay. Classical semantics. Slide set 2. Predicate tautology is much more complicated, so the laws of quantifiers are much more important. So, and all depends how you interpret all those symbols. So, and we defined Now, two things. As we did in chapter 2, there's no change, that we define interpretation, and in the universe. So we defined a structure, MUE. I am going to write it because this is important. Structure, MUE. U is universe, and E is interpretation, and universe is non-empty set in that universe. And that's what we're going to define satisfaction and truthfulness in terms of a structure and interpretation. And of course, we have our language, which have our connectives and our P, F, and C, right? And what it means that we need the interpretation interprets, okay, interpretation, E, interpretation in U, interprets, it means represents predicates, P in predicates, as relations, real relations in U. So P, E is a real relation. Now, if F is a functional symbol, F, E is a function on U, and C is a constant, these are symbols, and CE is element of U. So this is in the structure that becomes a real function. You interpret a certain real function, certain real relation, and certain real element. Constants become elements. And now we have a classical semantics. It's not only classical semantics, but also it is a classical definition of classical semantics, and for predicate logic. So it was defined, it is built up after Tarski, 1936. He was the first who really formulated properly and formally the semantics of predicate first order logic. So, and this kind of definition uses 3 points. So we have a structure, we already have it, with interpretation. The second part is assignment S of L, I'm going to explain, and satisfaction direction. So I already talked about the structure. Now we'll talk formally about it. Assignment S and satisfaction relation, and the definition of the structure, the assignment S, is common to different predicate languages, and for different semantics we define them as follows. And here it is, a structure, MUI, U is non-empty set called universe, and I is assignment called interpretation of the language of the universe, and the components, everything is here, and now you have nicely written in now what I said, that Pi is a relation. It means Pi is a subset of U to the power n. If P is an element relational symbols, for the function is a real function, which if f functional symbol has an argument, the function has an argument, and constant is just element of the universe. So an example, it's a nice example. For example, you have a language which has one relational symbols and two argument relation, and I have the U 1, 3, 5, 6. I pick up some numbers. So the predicate R, Ri, I interpret in this set as less equal relation. And then I have the two-argument function, and F is one-argument function, and C and D are constant. So, and here's function. I say that F is one-argument functional symbol, so the function would be a concrete function given by a formula. So Fi is a function which is universe into universe, and I put the formula Fix 5 is 5 for all because I'm lazy, and G is two-argument predicate, so Gi is two-argument function, and I put, again, I'm lazy, so I put the formula for this G is Gi of xy equal 1 for all x. And the constant, I say, is 3. And constant D is 6. And now my structure, we write it like that. So now the structure is, this is universe. Now the predicate is less equal. The function defined by that formula. The function G is defined by that formula. Constant is 3, and D is 6. So I defined our structure. So the second part, which is very important, so given our language with the set of variables, we defined assignment of language in the structure. Is any function S which takes variables and returns elements of the universe, and I want to write it here because I will be using it in a second, so I want to have it. This is called assignment of our language L equal L P F C. Assignment of L in M is any function S for assignments, as assignment, double S is S. I'm just kidding. Variables into the universe. So each variable is an element of the universe. It is called also interpretation of variables in a structure M. Now, of course, now I have a set of terms, and I know that variables are terms, so I want to extend that assignment to the set of all terms. So I want to extend. I know that variables here are terms, T, and here you have variables. So now I want to extend S to extend. Now I want to extend S to all terms. Extension, because I have here, I want to see what's happening. Also, we use the symbol V and V star for extension. Now I want this extension I denote as I, because here is an interpretation of that you called interpretation of variables in M, and now this extension would be interpretation of terms in our structure. So SE would now take all terms and return. So that's why we use that symbol. And we do it by induction over the term. So we extend is to from term to u as follows. And now you have inductive definition. Of course, for any x variable, that's a typo, like with normal extension, as interpretation of variable is what it was, and now interpretation of constant is whatever was interpretation of constant. And when you have terms as f, and f is the functional symbol, so as f of f t1 tn is a real function in our u of that inductively, recursively already defined on as interpretation of T1, interpretation of Tn, and so on. So it's typical recursive definition. And here's an example that, again, we have a little language, and we have Z is the set of integers. Interpretation is f is given by formula fn m plus 1. H, our h is given by formula fn mn m plus 1. Here fm is one variable plus a constancy, and fm two variables m plus 1 for all. And now S assignment, our S is variables, so S is from variables to Z. That is our universe of interpretation. And I put on X -5, on Y 2, and for T1, T2, I put T1. This is my T1, this is an example, and this is my T2. And now I want to evaluate S interpretation of T1. By definition, as SE of T1 is H, I put H y f f x. You see, I always find little typos because it shows that I'm thinking when you see, I said, oh, here, y, h, and here was ff, and here's f. So that we have to change in example, not double f, but just f. Will be updated. So assume that T1 is this, so then you evaluate, you have H interpretation of H1 on S1 on Y, SE of Y was 2, and SE of X was -5. So H was plus, because we had the H, you see the function H, HE was plus, and FI was also +1. So you have that that becomes 2, and that is f of -5. So I get -2, and similarly I evaluate. So that's how you evaluate. So observation, and this is also another important moment, that if you take that x1, xn for a given term are all variables in T, we write that T is x1, xn. So now if we write like this, it means like with the propositional formula, we were writing a, b1, bn, were all variables, propositional variables in the formula. So this is all variables appearing in the term. And for any term and a structure and any two assignments, we have the following. If the assignments are the same as an S prime on all the variables in term, we say that if and only if they agree on the variables appearing in T, so Si of T is S prime I of T. So if they do agree, which we defined before, we have that property. So for any, that's another important notation. And I'm going to write it because we will be using it soon in the definition of our satisfaction. And now, given a structure, and you have S now is, remember, into U, we write S, this S, A, X, is assignment, this is assignment S prime, which takes variables in U such that, so this is S prime, such that S prime agree on all variables except on X such that S prime X equal A, this A, for certain A in U. So that is our any assignment S prime with the property that S prime in S agree on all variables except for this X, and this S prime has on that X value A, we write AX. So this is important notation because we will be using it all the time. So, and now we use the satisfaction relation. Satisfaction is that structure M and assignment S satisfy A, so it acts between structures, assignments, and the formula. And also the satisfaction relation allows us to distinguish one semantics for a given language from the other, and consequently one logic from the other. And now we do it for classical logic and to define the classical predicate tautology. So satisfaction given a first for any now given a first order language. Now our PFC are countably infinite sets, all non-empty, so we have as rich language as possible, and let M be a structure for that language and S be any assignment L in M, and for any formula we define a satisfaction relation which reads assignment S satisfies the formula A in M. So S sat S, this assignment, satisfies A in M. Before we had just V satisfies A. Now we have assignment S satisfies A in the structure, and you do it by induction. And that is a totally classical definition. First atomic formula, we say that structure S satisfy atomic formula in M if and only if whatever the interpretation was on Si and T1, etc., is in interpretation of, so that it says exactly what our interpretation in M and S tells it to do. And if it's not atomic, it has one of the connectives as the main connective. And remember, we use our language connectives. Language has classical connectives, our favorite set of connectives, and you have PFC, right? So, and we go negation, if not, did not satisfy, conjunction, and of course our meaning of and is our truth tables for and so on. This is how you rewrite the truth propositional truth tables for implication. So it's a typical. And also now, if it's not atomic formula, and A begins with one of the quantifiers, so M satisfies for there is XA if and only if there is S prime such that S and S prime agrees on all variables except of S, that M S prime satisfies A. And so there is the quantifier there is assignment such that S, this S and that assignment agree on all variables except for X, and that S prime satisfies A. And for all, it means for all S prime such that S prime agree on all variables except for X, you have M S prime satisfies A in the structure M. And also the truth and falsity of the statement S satisfies A in the structure M depends only on the values Sx for variables which are actually free in A. So that's why this condition, last condition, we write like this. So, and that is another, it can be taken as another definition of that part of satisfaction, that Ax with free variable is a formula with a free variable x, is not atomic, and begins with one quantifiers. So you see, I put, you see here, I don't say if this x is in A. So now I take A where x, I have a statement ax, so this is like really this quantifier binds that variable in A. So we say that S satisfies that formula if there is S prime such that Sy equal S prime y, such that for all variables which are not x, S prime satisfies S. So, and again, for all would be for all S prime, and so this is more like straightforward definition, so we'll be using that. And then you have, okay, so now I wrote few exercises, there's more in the book, because just to give the feeling how you work that definitions out. So for example, we have two structures, an assignment, and defined an interpretation like that. M1 is 1, Q1 is equality, C1 is 1, M2 is now universe is 1, 2. That's a very big universe, and this is a little bit bigger universe, and relation is less equal, and here was equal, and I take the same constant, and I have a very simple atomic formula. So in this, and the first structure, so all assignments are like that. You don't have more assignments. So as all variables go, because universe has only one element. So it must be defined as x equal 1 for all variables. So SE of 1 would be SE of x is 1. SE of C is, by definition, interpretation of C, which we put 1. And so by definition, M1 S, this S, satisfies that formula if and only if SE, by definition, X and SEC is in QE. But what does that mean? SEX was 1, so it means 1, 1 belongs to Q, belongs to equality. So what does it mean that the tuple belongs to equality? It means that 1 equal 1. So we prove that M satisfies Q for all assignments. That is, and then the other one, I have a little bit bigger, but I'm lazy, so I put that as x equal 1 for all variables, so I keep the same s. And now what's happening? I have the relation qi is less equal, so I have six and sic. I put c is 1, would be that 1, 1 belongs to less equal. It means 1 less equal 1. So we have found such S that S satisfies. And in fact, we found uncountably many such assignments, and think why I wrote this sentence. And another structure, and we have another, now we have let's have a structure, and S prime is such that S prime x equal 2, so we evaluate S prime I of x is 1, and SIC is 1, and we verify whether S prime, this S prime, is in Q1, so it means that 2, 1 has to be in the relation less equal, but it's not true that 2, because 2 is not equal, 2 is not equal, less equal 1, so we found as different as S prime that MS prime does not satisfy our structure. And again, in fact, we have found uncountably many such S prime. So, and now we have a model, normal definition of a model. M, a structure, is a model for a formula if and only if MS satisfy A for all possible variable assignments. Because S satisfies, so if all S satisfy A in the structure M, M is called a structure, and we write it like that. And again, if you have set of formulas, we say that M is a model for a set of formulas, it's a subset of formulas. If M is a model of A for all A in the formula, and again, a countermodel if there is assignment such that it does not satisfy. Countermodel. Countermodel for a set of formulas is, as we do, M is not a model for a set of formulas. It means that there is A for which in the set, formula in the set gamma, for which M is not a countermodel. And now, okay, observation, because that a formula, when a formula is a sentence, then the truth or falsity of the M satisfies A is independent of S, because there is no variables in A. So if M satisfies a formula for some S, then it holds for all S. So we have a fact that if A is a sentence and there is S such that MS satisfies A, then M is a model of A. Because model, it means for all S. So if you have one S for the sentence, it's true for all S, so it is a model. And what we do, because having sentences makes the whole work a little bit faster. So we define a closure of a formula. A closure of a formula means a formula obtained from A by prefixing in universal quantifier all variables that are free in A. So it means if A does not have free variables, it's a sentence, the closure of A is defined by A itself. So in this way we can just close all the variables and deal only with sentences. And here's an example. If you have a formula, it has 1, 2, this is bounded, so you have to here is free, so I bound it, and here I'm like looking. That is bounded here, but it's not bounded here. So you have also to bind all. So the closure would be all the sentences. The same here. The closure would be you just put you bind all the free variables in one and the second formula. And here I gave you more examples, and more examples. It's good to have a lot of examples because in this way you can just look at it. So, and we say, that is again important statement. We say that given a structure, we say that A is true in the structure. Because before it was M and S satisfies A. Now we say A is true in the structure, and we write it like that. If for all assignment S, M satisfies A. So, and then when it means we write M satisfies A, that it means when M is a model of A. And A is false in M if and only if there is no assignment such that in M that there is no assignment S that satisfies A. So you see, it's okay. Let's write it like that, because we have M S satisfies A. We know what S satisfies A in M, and now we have M satisfies A. So we say M is a model for A. What does it mean? That holds for all S. So you skip this S and you say that M is a model of S. Is nice. And also you say that M is a model, and you say A is true in M. Like we did in propositional, V satisfies A, and then we write A, we skip V if it is for all V. So we use so tautology. For all V, we skip the V, defining tautology. So now we say that M is a model. We write this if MS satisfies A for all S. So this is in a similar way. And we write symbolically. So let me also read it. A is true in M and M is false in M. We write like this. And because we have intuitive understanding of notion of satisfaction. And you have different properties, that A is false in M, if and only if negation is true, So M is false in A is false in M if and only if negation is true, M is true if it's classical logic, so you can see by definition you have all those properties, very nice properties. A is true in M, and M is true in A and B, then B is modus ponens, you have correctness of modus ponens, and you say that A implies B is false in M if and only if that A is and not B satisfies. M is a model for A, so A is true, and M is model for not B, so false. So implication A implies B, negation was A and not B, so that is A and not B, and this is does not satisfy, and of course, M satisfy A if and only if you can put a quantifier in front. And so it means that A is true in M if and only if the closure is true in M. And we defined formula, a predicate tautology is valid. I use the word propositional and predicate tautology, but we use in predicate logic very often the word valid instead of tautology, not to get mixed with propositional tautology. So we say that A is predicate tautology, it means is valid if and only if M is a model for A, for all possible structures are models for A. And you see, so you say A is true in all possible structures, and that is the idea of tautology. What does it mean that something is predicate tautology? A statement that is true in all possible structures, in all possible interpretation, is always, that is always true. So we can always use it, whatever we said, we can always use it as a general law of our logic. And we write P here for predicate tautology, because I keep using that to distinguish this is propositional and this is predicate tautology. And so to distinguish propositional and predicate, and then you can have the set of all predicate tautologies. And of course, formula is not a predicate tautology if there is a structure such that M is not a model of A, so it's called a contramodel. And then it's not predicate tautology, it means that we have a contramodel. So to prove that formula is not a tautology, we have to find a contramodel. It means you have to define all the components of the structure. You have to define the set, interpretation of the universe, and also define, because you need to have you need to also to define the truth assignment such that MS would not satisfy A. And we say, and also we can introduce the predicate contradiction if A is false in all structures, and we use the contradiction A if and only. You can write P here also. So you see that is, you write P to distinguish the propositional and predicate contradiction. And of course, you have A is tautology if and only if, negation is a contradiction, and is contradiction if and only if it's tautology. And now we can prove, like for example, that that is predicate tautology. For all XAX, there is XAX, and here it means that for all that there is, assume that is not a tautology. It means that you have a structure and you have S such that it does not hold, and that is equivalent to this. And by definition, M does not satisfy for all means that MS prime on a X, you drop the quantifier, MS prime satisfy as X for all S prime, that S and S prime agree on all variables except of X. At the same time, ms does not satisfy the RIS XIX means that it's not true that there is S prime such that S is prime agree on all variables except for S, and ms prime satisfy X, which is contradiction, and we get the proof. And then you can keep going and now nicely proving different tautologies. So I want now to prove, for example, that the inverse implication, we prove that this is not a predicate tautology. It means that we have to tautologies for any formula X. So when you have a contramodel, it's enough to give one formula. This is not true for all formulas, so it means there is a formula. So I have an instance of the formula and we construct the contramodel. So let's take atomic formula, and P is two-argument predicate. So now I construct contramodel for that, because contramodel for that atomic formula, and we have structure N, and I take less, and C I take 3, and I will show you, and set is all natural numbers, and I want to show that M does not satisfy. And now we have to define truth assignment such that MS would not satisfy this. So let's say be any assignment into natural numbers, and let's S, and I want to show now that MS satisfy PXX. So take any S prime that on X is 2, and S prime Y is the same as we had before for Y in other variables. So we have that 2, 3 is in PI. It means that 2 is less than 3. So we prove that there exists S prime that agrees on X, not all variables except, and that satisfies. But at the same time, we have that MS does not satisfy that, but because, for example, let's take S prime 5. We get the 5 is not less equal 3, so that proves that this structure is contramodel. So we prove that that is not a tautology. And we have, fortunately, we have a shorthand solution. And we look at this, and we have N, P is less, C is 3. So this formula becomes, in the structure, there is n less than 3, then for all n less than 3 is obviously a false statement in a set of natural numbers. So because let's say n equals 3, etc. So that is a shorthand notation. So of course, when you construct contramodels, you do the shorthand notation as we did in propositional logic. I can let you use shorthand notation. And also, when you go back to chapter 2, that's how we defined the satisfaction, translating formula into the concrete formula. So you have plenty examples of shorthand notation there. So predicate tautologies, we know now what is a tautology. There's plenty of predicate tautologies, and they are very important. So I listed the most important, and with proofs, just because proving is a very good exercise, how you, of the definition of satisfaction as a model and structure. So I proved you, and I left you some as some of them as exercises. So, and also the restriction on certain tautologies. Here, when you look at these tautologies, yeah, you see, these tautologies have restriction. Where, for example, T is a term, is a result of substitution of T of all 3 occurrences of x in A. And T is free for x in AX. So you can do certain laws under certain very important, you just cannot say, I just put T. Here are the restrictions. So here also I show you that, that restrictions are essential. And here I give you an example why they are essential, because if you have restriction, you have to give an example that they were needed. And for the second is, again, I give you an example. So also I list you some very useful properties of that statement. Term T is free for x in AX because that term would appear in later proofs, in proof of completeness, and on different investigation of automatic theorem proving system will have that type of restriction. So I gave you some properties, because when you can understand, of course there is a definition and you can keep using the definition, but when you have some properties, you can better understand what that definition means. So, and these are important properties. For example, closed term T, the term with no variables, is free for any variable in X. Nice property, right? Any term is free X in A if A contains no free occurrences of S, and so on. So these are gives you a better understanding of that definition and the properties. And now you have more basic tautology. There is generalization law, which is very important. If you have B implies AX, so you can put universal quantifier here. And also, if you have BX here, you have to put existential quantifier. You have distributivity laws. And again, restrictions that AB do not contain free occurrences here. In the distributivity laws, here you have restrictions that if you don't say B and A here in all this do not contain any free occurrences of A, these are very important. And then I give you example why they are important. And here is that if you don't put it, the law is not true, you have counterexample. And now you have different distributivity laws, which are when you don't have the restriction. A and B have a variable, so this X binds here. The law says that you can distribute that over both of them, and the same, but in the for a universal you have different implication, that if you have for all XAX, for all XBX, you can pull the quantifier out. And again, for implication is you can, if you want to put quantifier, it goes, you can distribute universal over implication. And of course, the converse implication would hold, and models are provided, contra-models are provided in section 3. And also in chapter 2, I show you how to sort of understand those counterexamples, how to think about it. And of course, you have the Morgan laws for the formulas, and you have 4 of them because I used only the implication. So and you have nice proofs of the Morgan laws. So I gave you the proofs of the Morgan laws because at least that. And also another important laws are the quantifiers alternation, and which are intuitively, if you have there is for all, you have for all there exist. But of course, the converse, there is one for all there is one, that is good, but the converse does not hold, remember, and there's, again, you have a nice contramodel, and here is, like, for example, that take the structure real numbers and less, so you have for all y in real numbers, there is x, that x is less than 1, and it's not true that there is x that for y x is less the y, so you have the contraband. And also the important part is equational laws of quantifiers, as we have and we defined logical equivalence. Now we define like that, because you can do it like all models of A are models of B, etc. This is a simpler definition. We say that A is equivalent B if implication in one direction and implication of other direction is a tautology. If you introduce if and only if, of course, if and only if is always defined by A implies B and B implies A. You can define equivalence in terms of equivalence connective, but again, equivalence is just a symbol. It's not a connective. And of course, you have tautology's theorem if formula is. Now, okay, so you have equivalency. Now, how you get more tautologies? I gave you the whole list of different tautologies, how you have easily get a lot of tautologies, how you construct predicate tautologies. Of course, if A is propositional tautology, then substituting for propositional variables in A any formula of the predicate length, which we obtained, of course, a formula which is a predicate tautology. And moreover, then you can have that if you have two propositional equivalences and A prime, B prime are formulas of predicate obtained by substitution of this, so the substitution also would be equivalent. And here you have for example, we have propositional logical equivalence, and I put a formula for this and I put formula for that. I get by equivalence theorem, I have such a nice complex. So again, if you see such things like, you can look at the structure and see, really, that is this. This is, so you can go from here to there and you say, okay, that is a predicate equivalence, because that was a propositional equivalence in different. And then you have, like similar as in propositional, you have equivalence substitution theorem, so that you can work on the equivalences. You can treat really this equivalence as equality. And so more important logical equivalences, that if you have two formulas, A is x is equivalent bx, then you can put on both sides or universal quantifier or existential quantifier. And now I'm listing you equational laws for quantifiers, because they will be very important to use it doing scholemization, which is in the chapter 10. So we need to know, you need to know those equational laws of quantifiers. Of course, we have to prove it. So now we write the Morgan law as equational laws. We write definability laws, that universal quantifier can be defined in terms of negation existential through the Morgan law. That's why in classical predicate language, you might have classical predicate language only with one quantifier and define the other in terms of this, or you can have only this quantifier and define universal in terms of that. But we use in our framework both of them, because that's how we think. And here, a nice proof. So you want to prove this, you substitute for formula A, and you use the propositional equivalence. So this is a propositional equivalence. So we substitute for AX. I get AX if and only if logically equivalent to dot dot A. From that you get this, and then you have E theorem. So you put E in E on both sides. By De Morgan law, you have that E of this is, you put the in front, and by substitution theorem you had this. So you can play that nice little and here are important equational laws. You have, I listed them. So remember, when B does not have variable x, so you can, you see, distribute all quantifiers when you have the second formula does not have a variable x. So this is called introduction and elimination laws, because in this sense you can introduce, and here you can eliminate by putting here. So they are called introduction, provided B does not have variable x. And again, you have more introduction and elimination laws. It means that you want to when you want to distribute over implication, universal becomes existential by De Morgan law. And so, of course, this for implication you can nicely get from all this disjunction, conjunction, and De Morgan law. So you can play with them. You don't need to remember all of them. Like, for example, I want to prove this law. So what I do, I replace this by universal, and now I have this. I do De Morgan law. This is OR, so I do the De Morgan law, and now I have, and now I can distribute. I know that I can distribute this over here. So so I get this, and now I do again this negation over that is De Morgan law. So I have this, and I have double negation, and then this is B, and that is the risk. So I prove that. So what I'm saying that they are not independent. You can get some of them from the others, and so on. It's a nice. And also you have distributivity law, where A and B are free variable, both have. You have conjunction. Universal quantifier is distributed over conjunction, and existential is over disjunction, and equivalence does not hold otherwise. And then also you have alternation of quantifiers, that you can change them, and you have renaming the variables, which we'll use a lot, that if you have for all xax, you can rename the variable for both of them x, and you can remain x, and that will use a lot of renaming. And also you have restricted De Morgan laws. So we are that, and you can prove it by definition of rewriting. So if you want to use restricted, De Morgan law holds for restricted quantifiers. Very nice, and I proved you this. It means that bx for all bx translate into implication, and implication you translate not B or A, and then you do De Morgan law, and then you do De Morgan law inside, and then you know that would be the risk bx and not ax. And by definition, you translate, this is translation from normal to restricted, and you have so De Morgan law. And of course you have different that's what for example, if you have restricted, if B does not have variables, they behave as normal quantifiers. So these are good, safe laws, but those all equivalences do not hold. So again, proof by constructing contramodel that for normal quantifiers, all of them holds. If you have restricted, they do not hold. And in chapter 2, I gave you also the how you can fix it to have equivalences. And okay, so all this, I just want to end almost by formulating a completeness theorem. It means I put the definition of a proof system. Now we have a predicate language. Our definition of a proof system, as we defined before, is exactly the same. Proof system is a language. Now is this language, set of formulas, logical axiom. Hilbert proof system has a modus ponens. So we have what we have before. Logical axioms is not empty of now predicate tautologies of that particular language, and we use these are predicate tautologies. This is a particular tautology, and we say that, of course, the rule is sound. You say the rules are sound if inference rule is sound, if and only if, for all structures, if M is a model of the set of all premises, is a model of conclusion. So we, and for example, that is not a sound rule because for all x, okay, of course, this for all x, ax, there is a sound rule, right? Because so assume that it's not sound, it means that there is a structure such M is a model for this and it's not model for that. So what does it mean? That MS satisfies this and MS does not satisfy that. So it means that there is S prime such as agree on all variables except for x, and it's not true that there is S prime such as S prime agree on variables of x, and MS prime is a model for a S prime satisfy AX in the structure M. It's impossible, so you have a contradiction, but you can see, I know that for all X implies there is X. We already prove it as a predicate tautology, so you can say, okay, this is, but that is really the proof. I rewrote the proof for the fact that for all X, AX implies there is XAX is predicate tautology. And this is not sound. You give a simple contramodel. And again, for the contramodel, you have a shorthand solution that if you have this formula, you take the structure natural number less 3, you have there is n less than 3. So it becomes mathematical structure for all n, which is a false structure, so the rule is not sound. And of course, we need to have the strong soundness for our automated theorem proving. So it again is strong sound if it is we carry M as model for all premises, if and only if it's a model of construction. And for example, this rule is strong sound because this is the Morgan law. And we have the sound proof system, and we have soundness theorem, which we write that PS, all probable, are included on tautology, and you have completeness. Proving soundness is easy. Completeness is even more complicated than in propositional. So, and completeness theorem, if is proof if and only if is a tautology. So that is a shortest way of formulating completeness theorem, that PS equal TP, and that will be our goal next time. Chapter 9 is a proof of completeness theorem for classical predicate logic. And that's it. So next is a proof of completeness of classical Hilbert-Stein classical predicate logic. And of course, we have two proofs of completeness theorem. One will do Hilbert-Stein. We did two proofs for classical, and next step we present a standard proof for Hilbert-Stein proof system in the chapter 9, so that is our next goal. And in chapter 10, we will do automated theorem proving system QRS and prove completeness theorem for that too. And you will see how much easier it is when you deal with Gensen-style theorem proving systems. So that would be chapter 10. Thank you very much. That's it.